Sure. Okay, so we are talking about a list of things. The first of which we just got done talking about is, okay, when do we get acceleration centripetal? Acceleration is just the change in velocity over time. If acceleration is perpendicular to velocity, okay, then it will change direction. If it changes direction consistently from staying perpendicular, didn't draw a great picture, then it should make a circle. If it makes a, I didn't finish this actually, so it's a good thing we're redoing it. If it makes a circle, there's another nice thing that you can say about acceleration. Okay, it's not the first thing I would say about acceleration, but if it is in a circle, you can also see, in addition to being perpendicular to velocity, acceleration is pointed towards the center of that circle. That's what the word centripetal means, towards the center. Its counterpart, which we will get into my frustrations with not frustrations, that's not right, the misguided nature of it that some students struggle with, is centrifugal. Centrifugal, you've heard of a centrifuge, okay? You've heard of potential centrifugal force, and a lot of people think it, even though it's 100% incorrect. We'll talk about that a little bit later. But yeah, centripetal acceleration is perpendicular to velocity. It is also, if I had drawn a great picture here, this should be perfectly circular. It's not. It should also be pointed towards the center of the circle because of the things we just said. Cool beans? Cool beans. All right. What does velocity tangential mean? Anybody want to give it a go? Guys, we're at the beginning of the chapter. Don't feel bad about not knowing. Just I need somebody to throw out an answer so that we can work with something. I need Clay to work with here, right? Okay, Chloe. Question is, what is velocity tangential? Okay, or how is it the same as standard velocity? How is it different than standard velocity? What's the tangential part mean?
I was gonna say, is it the like omega times radius?
Yeah. I mean, there's an equation for it. Sure, you're not wrong. That is absolutely part of that. That's not quite what I was looking for, though. Go ahead.
Is it like, so like the vector of like velocity would be like tangent, it's like the tangent line, you know?
Yep.
To something, the circle.
Yeah, absolutely. Okay, so that's a great place to start. 100% right. Okay, it's tangent. The velocity is tangent to the circle. Okay. I'll come back to that in just a second because there's a couple things I want to cover first. But yes, that is 100% right. Trent. So that's the other thing I wanted to hit. Yes, and yes. Okay, so the tricky thing about velocity tangential is this. If I were to draw the thing going around in a circle, let's make it go counterclockwise this time. Okay, I would draw it tangent. I would draw it tangent. What would be the case with those two arrows? Sure, it's not quite what I'm looking for. That is true. They're the same size, meaning they are the same speed. Okay, so velocity tangential is weird because it's a speed, right? So you go, wait. A speed is just magnitude, right? A velocity has direction. So what's the difference between velocity tangential and a speed? Well, it is a speed because it's staying the same size. But you'll remember, acceleration is a change in velocity. But two things of velocity can change. Can you have acceleration and not change speed? Yes, if you change direction. So, yes, velocity tangential is the speed it's at. So why do we call it a velocity? Because it still has direction. It importantly still has direction because that direction better be changing. So it's a speed when we do things calculation and everything. So if I say I'm going around at 4 meters per second, you can say it's a velocity. And then the other really nice thing here is this. I can simply point out whether it's going clockwise or counterclockwise, give you a spot on the circle, and everybody knows the direction, right? What is the direction at that spot? If you had to point when it's going around counterclockwise, well, you would just say right down here. Does that make sense? So we don't give a situation like we usually don't focus on the direction because the direction is consistently changing. Does that make sense? Like I could say, hey, that's at 180, that's at 225, and that's at 315 as far as all of their angles, right? Straight that way, down in the third quadrant, down in the fourth quadrant right over here. I could do that, but it's kind of dumb because that number is going to consistently change all throughout. How are we doing there? Questions, answer,
Okay.
go ahead.
So, if those vectors weren't the same, like size, speed, whatever, it wouldn't be a circle, basically, right?
Correct, 100%. Yeah,
So,
it would not stay in a circle if those were all different. And we'll talk about that variation later on, but we're only going to deal with that conceptually. Okay? Most of our problems, especially early on in here, are going to be focused on absolutely perfect circles. Okay? Which is why I really focus in on what acceleration centripetal actually is, because students can get misled into believing it's always a circle, it's always a circle. No, it's not always a circle, it's always perpendicular, right? But if it stays perpendicular and they stay the same size, then it will be a circle every time. Yes?
So is the acceleration always perpendicular to the?
Yes. So if I pick a spot here like the ones you're seeing, I can tell you what direction of acceleration is in all of them. It's this way, it's this way, it's this way. 90, 90, 90.
Yeah, okay.
Now, like I said before, if it is in a circle, that does correlate with towards the center of the circle. Which is really nice too, because I could do this. I could say, hey, I have a velocity this way. I have a velocity this way, and my acceleration is going to go that way. What am I going to do? Well, it's kind of hard to kind of think sometimes about, excuse me, what 90 degrees is going to do. So what you could do instead is think, oh, it's going to make a circle. It's going to make a circle that looks like this, right? Whereas, instead, and we'll get to this in just a minute, if I have a velocity this way and my acceleration is this way, right? Not going to be easy to do, sure, but actually very possible, which we will talk about, okay? Which we'll talk about, actually, I'll give you a situation for it right now, okay? Because you're laughing, but it's 100% the case. That's the direction of acceleration on this bottom guy right down here. Its acceleration is upwards. Why is acceleration upwards? Well, because if it was 0, it would go straight that way, and if it was down, it would go in a circle down like this, right? So the towards the center of the circle thing, okay, is easier kind of to see what the circle should do, what it should do in real space. Yes?
So whenever we're doing problems like this, are we focusing on one point of the circle? Because like
usually
you could say like the other side of it.
Usually, sometimes not. Sometimes you can pick a circle. Definitely with the more complex problems you're going to. All right. Here's my list of stuff I need to cover. I need to cover talking about stuff that and a lot of this is review, but also kind of combining it all together. I'm not going to be able to hit all of this today, okay? Because quite frankly, we lost some time on talking about the test. But also probably more importantly, like these are big subjects that are kind of confusing and you need to be asking good questions, and that's just going to take some time. So let's start with the top one, okay? Arguably the simplest. What is that equation that you're looking at up there? What is that equation? That's Newton's second, correct. Newton's second. Newton's second essentially was the nutshell of how acceleration is caused, and that has not changed, okay? I've said it a couple times yesterday, and I think I started at the beginning, centripetal acceleration is not a new acceleration. It's when the old acceleration does this thing, changes direction, okay? In your chapter, you're regularly going to hear about centripetal forces. Same thing. This is not a new force. This is not added to the list of forces. This is when sum of forces causes this right here. Because I could say, hopefully we're on this page right now, hey, velocity is that way, okay? What's going to happen if acceleration is down? Okay, you should be able to tell me what is this thing going to do? It's going to change direction downward is the correct answer. And then if we assume that it stays perpendicular, you would then tell me, you would assume it's going to go in a circle like that. Yes? That wasn't bad. Okay, it takes a little bit of practice. Now, what causes acceleration? Force, right? So, in order for acceleration to be pointing down, what must be the case? Net force better be pointed in that particular direction. Now, hopefully this makes really good sense, because one of the examples I gave you on Friday, you are running, You're running on the playground and you want to change direction. What did the person do in order to change direction? Gravity. Providing what force?
Tension.
Tension. Tension is now pointed that way. There are no forces the other way, so there's an unbalanced force on me going perpendicular to my velocity, and therefore what do? I change direction, I change direction, I change direction, causing a similar tension until, what do? I let go, no longer causing a net force, so what does my velocity do? Follows inertia. It just goes the way that it's supposed to go, at a constant velocity in the same direction. So what I'd like you to do right now in your group is I have 4 examples of forces over there on the right side of the board. I'd like you to come up with as many examples of centripetal acceleration as you possibly can, and try, if you can't, to knock out one of those each time. Now, I wouldn't start with that. What I would start with is quite simply, especially if you're struggling with this, okay, kind of going against what I said earlier, think of things that go in a circle. Because if they go in a circle, that means there has to be a constant acceleration perpendicular, which means there has to be a constant force going perpendicular. So think of a situation where they go in a circle, and then try to figure out what force it is that actually causes that, okay? Like I said, as many examples as you possibly can, but as best as you can, try to knock out at least one of each of these. And if you can't, we'll go over them in just a minute. Discuss.
I mean, you can argue this.
If you'd like to know them in order of what I would consider probably easiest to hardest, these 2 are probably your easiest, followed by that guy in terms of finding examples of them.
If it was attached to a wall. What about force friction? I don't know.
All right, give me an example. Example of centripetal acceleration, go.
Gravity. I mean, orbit.
Okay, orbit. So there you go. So the situation is orbit, absolutely. You're not going to get examples of gravity here on Earth. Why? Because gravity, for the most part, for us, stays the same direction. If it stays the same direction, there's no way for it to cause centripetal. So for gravity, in order to cause circular motion, it has to change direction. That's going to be on a big scale. So yeah, planets orbiting around the sun, gravity. Satellites orbiting around us. So this is an interesting conversation that you get into with students that kind of like, I kind of ignored until this particular subject. Is there gravity on the International Space Station? There definitely has to be. Based on what we just said, why? Because if there wasn't, it would go straight. So then there gets to this weird conversation that you have to consider, like I've seen video of people in the International Space Station, there doesn't seem like there's gravity, so I'll let you kind of worry about that as we get into that. Well, that'll be actually in conversation 3 up there. All right. So, what else? Yes?
That's kind of a guess, but like a wheel of a car being force normal?
You're going to need to be more specific there because yes and no. You're not wrong yet.
The one that is yes is the one I'm
Now, do you mean the wheel revolving around itself?
Yes.
Like if I just took a wheel and spun it?
I meant like the wheel of a car, but if the one you're saying.
I heard the wheel of a car, yes.
I feel like
the wheel of a car could be like 3 different things
like
depending
if
on
you're
how
going
the
in the
context.
car wheel is, you're like driving the car.
Yes, you're driving the car. What does the car do?
It's going forward.
Unhelpful right now. Okay, so if you just focus in on the wheel of the car spinning around itself, it would not be normal. What would, in the same way, basically what you're dealing with is I'm going to sound of music you right now. Okay, my arms are going in a circle. What force is on my arms that was forcing them to go in a circle? Tension. You would call that tension that holds you together in that particular case. So you would say tension. Now that's not usually an example that we regularly deal with. We'll come back to the car example probably here in just a second. Also, interesting thing about spinning around like that, and I would highly suggest doing it if you're embarrassed by it on your own. There's an interesting thing where you can actually kind of prove this equation to yourself quite simply by spinning faster and faster and faster and faster, because the faster you spin, this equation means there should be more acceleration, right? And if there's more acceleration, that would require more force. So what should you feel like your arms do the faster you spin? They feel like they get they arguably not exactly, but heavier. And they're not. They're not heavier in the slightest. You can pull this same, if you want a better, probably an easier thing, take a couple of books or masses. I'm going to do my best not to fling these and discus at some of you right now. Okay? But you can feel kind of like how much force you have to pull, and then if you pull hard, faster and faster and faster, you can feel the greater amount of force that you have to put on these things the faster you spin, because there's more acceleration, and more acceleration means there's going to be more force. But I digress. Other situations.
Okay, I have a question. What would a Ferris wheel be? Would it be like the gravity?
I would say tension in that case. Yeah.
But like gravity's pushing this.
Is gravity changing direction? No. The fact that gravity is there is not. So, whenever we are looking at these examples, specifically, you are thinking about an object going in a circle. So this is kind of the hard conversation that we had a little bit on Friday between rotation, okay, and changing velocity, right? When you think of a Ferris wheel, you think of the entire thing rotating around itself. What I want you to think about right now is kind of that the piece on the edge of the Ferris wheel, there's a bolt on the end of the Ferris wheel. What keeps that bolt going in a circle type idea? Does that make sense? I think that kind of helps a little bit more on why it's tension as opposed to gravity. Like gravity couldn't be. Gravity's at the center, right? And gravity is not changing direction.
Okay.
Yes, roller coasters are going to be huge for us in this particular chapter. Roller coasters would be force normal. I think you gave an example, Addie, on Friday of the insane. I think it's usually Tom's Twister, that carnival ride that doesn't exist anymore due to safety issues. They spin you so fast that you hug the wall type deal. You know what I'm talking about? Okay, that would be force normal as well. Yes.
For force friction, could you use like a bike chain?
Do what now?
Like a bike chain, like the gear part of it?
No, I wouldn't say friction does that. I think friction is, like I said, the hardest one to find, but sadly, probably the one that you use the most often. So I'll help you with friction real quick, because there's a whole conversation to be had here. No, Spain on, definitely still Spain on. Still both 5'6", well trimmed beard, but definitely Spain on. All right, here we go. Okay. What's keeping that in a circle? Let's knock out what isn't. Is gravity keeping that in a circle? No. Tension keeping that in a circle? No. There's no tension that's pulling inward here. Okay. Is there any surface? Is normal pushing it in a circle? No. It's friction, but it gets really messy with friction, and I apologize for this. There are two types of friction. What are they? You also. First, I did that same thing. Skipped ahead of me on that. That's fine. You're getting ahead of me, but technically there's two before that. The two are air and surface. Which one are we dealing with here?
Surface.
We have a surface friction. Yeah. Now within surface, there's two types, which is static and kinetic, moving or not moving. So, which one's this one, guys? Yeah, it's weirdly static, but you look at that and go, it's moving. Why is it static? So answer that question. Why is this static friction if we're watching the thing go in a circle?
It's stationary, but under its moving.
Yeah, you look at the materials compared to each other, right? Are these moving relative to one another? The other thing you have to consider with friction is this. Kinetic friction only ever goes one way, the opposite of the way the object is moving. If this thing's coming out at you and it was kinetic friction, can kinetic friction cause circular motion? No, it can only cause it to slow down, right? And And you get this, by the way, you actually saw it a second ago when I go too fast, or if you go too fast off the interstate, or if you go too fast on ice and you want to change direction. What happens is you then start to slip. And slip means you are in kinetic because the materials are moving relative to each other. And if you're slipping or moving relative to that material, can you control the direction of your car? No. The only thing you hope is that it slows down and stops. So what type of friction is this? This is static. And static gets a little bit weird, so let me just remind you a couple things real quick. Static friction, not worrying about circles. I push this guy. Which way is static friction? To your left, yes. Okay. And which way now? Okay. Now, the other weird situation I shared with you was this. Okay, I'm putting this in my hand and I'm taking off. What force is it that goes that way to give it acceleration? Static friction. So which way does static friction go? The opposite of the way inertia wants to keep it. Right? Which way does inertia want to keep? What does inertia want to do to this thing? Keep it stopped, because that's what it's at right now. Right? So if I push that way, it goes the opposite. If I push that way, it goes the opposite, keeping it at inertia. Which way does force friction point here? Sorry, which way does inertia want it to be? It wants it to be stopped. So if I take off, which way does static go to oppose that? This way. Meaning it wants to, like, if I go too fast, it wants to stay stopped. It's the tablecloth example. Now, when I go in a circle, from the perspective of the circle, the object wants to go to the outside. So which way does static friction point? Towards the inside. And sadly for you, also good for you, this is like the most common one that you use. Here, let me demonstrate real quick. I'm going to walk in a circle. What force was it that kept me in a circle? Friction. And if you don't believe me, when you do that today, when you go, especially if you go in a tight circle, if you try to go quickly and you need a lot of acceleration and therefore a lot of force, here's what you're going to find yourself doing. If you pay real close attention to your feet as you're going in the circle, what you're going to feel is that your foot is pushing towards the outside. Why is your foot pushing to the outside? Because that way static friction will point towards the inside part of the circle. Don't believe me? Try to wear slippery shoes and go in a tight circle. Without friction whatsoever, are you going to be able to pull off going in a circle? No. All right. So we're going to begin this conversation, although it's a big one, so we're probably not going to finish this one here today. We want to try to, the goal right now with this equation is weird, okay? Acceleration centripetal is equal to VT squared over R. Okay? What I want to try to do in this conversation is convince you that this is the old acceleration. This is equal to change in velocity over time. The first thing to help out, I already started talking about on Friday, and it's this. If I have a car going this way with an initial velocity, and then it has a velocity going that way, it's obviously sped up, right? In other words, what I want you to do is I want you to focus on the change in velocity vector, okay? Whereas we used to look at this equation and see this, two different values and time. Why is that equation not going to work in circular motion? The speed doesn't change. So what is that going to tell you acceleration is? Zero. And that's true of speed. But is there, in fact, a change in velocity when you change directions? Well, let's look at the picture real quick. Here, I've drawn my initial velocity, and 45 degrees later, I'm going to draw the arrow the exact same size. Is this the exact same size of arrow? Has speed changed?
Yes, no.
Well, speed has not changed, but has velocity changed? Is there a change in velocity vector?
Yeah.
There it is. It's that vector divided by time that is what we're looking at right here. Okay? Now that was easy to do with numbers. It was easy to say, hey, this is 4 and this is 10, so change in velocity is 6, right? And then you can take that 6, divide by whatever time, 3 seconds, and get your acceleration. We've got to find a new way to find that. We'll do that tomorrow.
Stationary